All right. So last time we talked about the repeated eigenvalue and also zero eigenvalue case, which basically wrapped up everything we have learned so far in solving system of linear equations in 2 dimension using a matrix representation. Okay. Now I think it's time for us to go back and revisit what we had from second order differential equations, which we already know it can be transformed into it can be transformed into a system of differential equations. So we want to talk about the harmonic oscillator. Okay, we have something like this before. M A equals Hooke's law minus a B y prime. So this part gave you the spring, Hooke's law, the spring force. This part gave you the friction. Okay. Now what we have is basically a system look like that. By prime plus ky equals 0. So that's what we got from a general harmonic oscillator with friction and also a spring. Now, what do we do before if we want to solve this? Well, the first thing we do is we change it to be y prime prime plus py plus qy. Y prime prime plus p y prime plus qy equals 0, where p equals negative k over m, positive b over m, and q equals k over m. Okay, and then we say, well, we guess our y is going to be e to the st, and then y prime is going to be s e st, y prime prime is going to be s square e to the st, and we plug everything in, so we end up solving this. As a quadratic. Okay, then we have this and that kind of problems, and we have basically another way to put all the solutions together, which kind of makes sense, which also is kind of shaky because basically you're just guessing everything, right? And suddenly it just worked. But now with all the theories we have done so far, now we can understand the same thing back. Okay, this is number 1. This time we can redo everything, but in a more careful version. That is, we want to resolve this time using every knowledge we just learned in chapter 3. Okay, so what are we going to do? We're going to let v equals y prime. Okay, then v prime is y prime prime. So what we have here is nothing but y prime equals v, and the v prime equals negative p y prime minus q minus q. Here's a y. That's why. What did I put before? I did have y. Okay, qy minus qy here. Now we don't want y prime, so let's erase this and replace it by a v. Then suddenly we got a nice system. Okay, equals v, okay, negative p y prime, which is v, and negative qy. So this system here for second order, and if we do a change of variable to let v equals y prime, can be transformed into a system looking like this. Okay, so how do you solve this system? Well, the first thing is I take out this matrix. And then I solve for the determinant. So determinant a minus lambda I, and I'm hoping this will give me my eigenvalue. Q. Now what is that? That is lambda plus P plus Q equals 0. Or we can say it's lambda squared plus P lambda plus Q equals 0. This is what we get from the characteristic equation. This is what we get from guessing. And now you can see they're the same thing. If I remove it here, what we had before is s squared plus ps plus s equals 0. Qs equals 0. So from here you can see they're exactly the same thing. Actually, your lambda equals s. So with all our guess before, what we were guessing is we're just basically guessing the format we did in chapter 3. That is, we're guessing the eigenvectors and eigenvalues. Okay, so no surprise, if you guess e to the st, you should get this. But if you do everything in terms of lambda, actually you get lambda first. But then you guess your solution is going to be e to the lambda t. Okay, so they are totally equivalent. From now on, you can forget about what we had before with s. We have a more careful version, and they look identical. All right. Now next, we raised the question before, right? How do we solve this system? Well, what we do is we solve a quadratic. We get a solution. We then know our solution is going to be e to the st. Okay, then we raise the question, what if we have, complex values? What if we are supposed to have two s, but we only have one s? What if we have 0 or things like that? But for now, well, that is nothing but, do you have two distinct real eigenvalue? Do you have two complex eigenvalue? And do you have, one real value which is repeated for twice? So clearly everything is covered as before. All right. Then with that, next time you see a second order differential equation, you can transform them into this and solve it using a system. With that in mind, do I want to do an example? Let's just do a quick example. Let's say this is what we get from a spring mass system. Somehow, okay, K over M equals 13, B over M equals 4. We just pick the number to be nice. Okay, so we got the friction. We got the spring constant. Now what you should do is you should simply just change it to B. Actually, we already have the formula, so I will just skip it. You can verify by yourself. Okay, 0, 1, negative Q, negative B. Change it to this. Then, what am I doing? Lambda I minus A. I keep switching these two. Okay, so switching the order doesn't change the value of lambda if you set it to be 0. So just to be fair, no matter which way, it's going to be solvable. So we have lambda squared plus 4 lambda plus 13 equals 0. That's exactly what we have here for the quadratic. If you replace prime by square, prime by square, prime by lambda, and so on. So which is negative 36. Okay. Now, what do we know? We do know we have two answers. And we need to set times the corresponding eigenvector. And we will rewrite them into real part plus an imaginary part with an I. And then we say this is our solution 1, this is our solution 2, so we can finish. Okay, so we don't have to worry about everything we had before, which we cannot handle. For complex values, this time we do have a way to do it. All right, I guess that's the example we need to go over. I will give you the answer. It's just recalculating what we had before. So y is going to be C1 plus C2 okay. All right. So computational wise, we already know how to do it, as long as we know how to transfer them into a system of ODE. The second part is more just clean up what we had before, a classification of harmonic oscillators. Okay. We do know that we are going to end up solving this. Okay. Then we do know that we're going to end up solving this eigenvalue problem. Then we know our lambda is going to be plus or minus. And we may have several cases. Okay, so what are the cases we have? Now, number one, what we're going to have is no friction, so B equals 0. Okay, if B equals 0, lambda is going to be 0 plus or minus square root of negative 4 km over 2m, which is square root of 2m squared. So it's going to be square root of k over m with a negative, which gives us okay. So this corresponds to what? This corresponds to complex eigenvalue. Okay. Moreover, your A, which is your real part, is equal to 0. Therefore, it's gonna be a center. It's not gonna be a spiral source or sink. Okay. Center. You go back and forth forever. You do not reduce to 0, 0 or generate to infinity. In this case, we give it a name. We call it undamped. Now you can see everything stay connected. That's the case, first case. Okay. Now, second case, we do have damped, but we want to further differentiate them into different kinds of damped. The first one is called underdamped. That is, you do have a B, all right, but you do have B squared minus 4km equals less than 0. This corresponds to a small b. So this is still, b squared is not bigger than 4km. In this case, what you will have is lambda is going to be this. Is going to be negative b over 2m plus or minus something with an I. Okay, so you still have two complex. Do you have a spiral source or spiral sink? You just look at the real part. The I part really just determines how fast you rotate. Note, b is bigger than 0, m is bigger than 0. Therefore, the whole thing is less than 0. It's going to be a spiral sink. So if you are underdamped, which means you are still going to oscillate, but you oscillate towards 0. Okay, spiral sink. So eventually you stop. That's called underdamped. All right. Now you keep increasing B. Now you have critical damped. Remember, increasing B is the same as increasing your friction, right? You are damping more and more and more and more. So no dump. Now a little bit dump. Now a critical damp, which means you increase B such that B is just right to make B squared minus 4km equals 0. In those kind of cases, what will happen? You will have lambda equals negative B over 2m plus or minus, but this is 0. Therefore, you are going to have one repeated real. Plus minus both give you 0. Okay, and it's negative. So what you're going to get is you are going to get a face portrait looking like a repeated. Okay, moreover, they're all coming in because your lambda is less than 0. Okay, that's what we call critical damped. Not this way. That's not smooth. I should do it carefully. It's this way. Okay. All right. Now finally, you keep increasing B. We finally have the overdamped. That's when you have B square minus 4 km is bigger than 0. Lambda, therefore, is going to give you and this part this time become real. Therefore, you have two distinct real. Okay. Therefore, you have something like okay. Now source node or a source saddle or spiral. No. Sorry, or sink. You need to look at is this one positive or negative, right? So now think about this. B is bigger than square root of B squared minus 4 km for sure. Okay. Therefore, negative B plus and this one minus are both going to be less than 0. So eventually you still got attracted to 0, 0. You are going to have a sink. Moreover, you go to the sink really fast. Exponential decay. This corresponding to in real life, what you have is you have a spring and you say this is where the spring is relaxed. So for how do I say this? Let me put it here. Okay. So for undamped, you just go here, go equal distance here, and then come back. You just go back and forth. Okay, that's undamped. Okay. For underdamped, which means you dump a little, what will happen is you are going to go here, but not as far. You come back, not as far, and eventually just go back and forth, back and forth, back and forth, and eventually you stop at the relaxation. Okay, that's for underdamped. Now, what do you mean by overdamped? Overdamped basically means you didn't even pass the relaxation and then you stopped because the friction is so great that you don't even complete one oscillation. You cannot even pass the relaxation, you just stopped. Okay, or maybe you pass this one, but without coming back, you just stopped. So you don't even have the capacity to have a sine cosine pattern. You just go here and stop there. All right, okay, that's where you have the overdamped. To see the solution, now let's try to take a look at first case. Undamped, you can see you don't have a friction here. So you have plus minus I with some frequency, okay, sine, cosine, no real parts, which means you have a center. Go back and forth. Okay, now you have a little bit underdamped. You have a very small friction here. Now you do have a lambda, which has a negative real part, and you have an imaginary part. So you are going to start to have rotation, and you are going to have a spiral sink because you have a negative 0.1 here. So everybody eventually goes back to the origin. Okay, now let's look at the oscillation compared to previous one. Previous one, you just oscillate. You should focus on the blue one. Okay, that's the displacement. No damped. Now it's damped a little bit, so you just keep going like this. Now critical damped. We are already familiar with the phase portrait. Okay, and you can see you cannot even complete one complete oscillation. You just stop at the relaxation really quickly. And overly damped will make this process even quicker. You You just start from somewhere and just automatically got attracted to 0, 0 without even coming back. Okay, see? It goes there really quickly. Okay, so that's roughly the classification of different kind of harmonic oscillators. You may ask me, like, what about the other cases? We still have spiral source. We still have, saddle or source in this kind of cases. Well, in general, that is true. In general, that is true. But it does not work for harmonic oscillator. Due to the special format of harmonic oscillators, if you look at the harmonic oscillator thing, negative Q and negative P. Okay? Or P and Q has to be positive because they come from friction. They come from a spring constant. Therefore, if you see something like this, it's very likely describing a harmonic oscillator, and therefore you're going to see one of the cases we described before. Okay? But if you see some cases like this, because all kinds of cases are going to create all the other cases, right? But as soon as you see something like this, you know it's not from a harmonic oscillator. Otherwise, you're going to have something called negative friction, or you're going to have some spring constant, which is negative. That is not real in real situation. So we do have other cases, just not for harmonic oscillators. And of course, if you want, you can go ahead and try to do them. The way to do them is quite easy. You start from a second order, but this time you don't have y prime plus this. Instead, you will have ay prime prime plus by prime plus cy equals 0, where a, b, c can be any number. It can be positive, it can be negative. For harmonic oscillator, your p and q has to be positive. Okay, so this will give you all the other cases. But still, you can change it to be, you can actually try to do it yourself. It's pretty easy. You can change it to be here. Okay, and this one is going to be negative c over a, negative b over a. But because a and c can be positive or negative, so and this can be any real number. That's where you get all the other cases. All right, that will be all for second order.